So extra example number 3. I said I was going to do D first, right? So this is a coaxial cable with current. So what we have is a wire, a thin wire, and current is this way in the wire. Let me just call it I. And then there's some insulation, and then coaxial with it is a cylindrical shell, like a hollow cylinder. Okay, so we're not interested in the thickness of this thing, but you know, it must have a little thickness to it, just like the wire in the middle. So this is a coaxial cable. And current, see, all of this cylindrical shell over here, right, has current I coming the other way, in the opposite direction. So oftentimes this is called the wire in the middle is called the gold wire. And the cylindrical shell where the current comes back, this is the return wire. The go and the return. It's like, you know, current is to the right down the wire along the axis, but then you have this cylindrical shell, that's metal, and current is coming in the opposite direction along that shell. And we want to know what is the magnetic field generated over here, inside the coaxial cable, and here, outside the coaxial cable. And so there are 2 regions in there. So this one here will be inside, and this will be outside. So for straight wires like this, the Amperian loop that we imagine is a cylinder. So I will the Amperian loop that I will draw when calculating the magnetic field inside is going to be a loop like this. Okay, so maybe I'll just do that. Of radius r. So this is the Amperian loop. So I'm going to say it like this. I'm going to say inside, I write down Ampere's law, which is B dot dl equals mu naught I enclosed. So inside the coaxial cable, well, the magnetic field, what will be the magnetic field becomes, it's multiplied by the length of the Amperian loop, which is what? What is the length of the Amperian loop? 2 pi r, and that equals mu naught. And what is the total current that goes through this loop in blue? What's the total current going through it? Just the current in the go wire, right? Because the other one is returning outside the loop. So it's just this. So the magnetic field inside is mu naught I over 2 pi r. Now, what about outside the coaxial cable? So outside, we write down Ampere's law. And if I want to know the magnetic field here, outside, what I do is I draw an Amperian loop passing through that point. So this is the Amperian loop that I imagine. Remember, there is no loop like that. And the radius of the Amperian loop is r. We want to know what is the magnetic field at a distance r from the axis of this cable, right? At some location outside the coaxial cable. And you've seen the coaxial cables in the lab, right? The coaxial cable are those that we connect to the oscilloscope input. Those are coaxial cables. So this becomes B times the length of the Amperian loop around, which is 2 pi r equals mu naught. And what is the total current that goes through this Amperian loop?
0.
Actually, it is 0, because you have the current I to the right down the axis, but it's coming back out on the outside, back out on this. So you have I going into the right and I coming back out. So the current I in the go wire, but the current in the return wire is in the opposite direction. So overall, the net current going through the loop is 0. So therefore, the magnetic field outside is 0. Do you remember of any problem where we had two things and the electric field outside was 0? What's that? No, but yeah, but outside of it, I want the electric field 0 outside of two things. The parallel plates. Remember the parallel plates we had like plus sigma and minus sigma? And we found that outside the electric field was 0, outside it was 0, inside it was from plus to minus, and this was sigma over epsilon naught. But it was 0 outside, right? It's like same charges but in opposite directions. Well, not opposite directions, opposite signs. In this case, when you consider outside, you have, the net current through this is 0. It's like having plus and minus. Well, because one of those currents is, to the right, so we can say that's plus, but then to the left it's negative, so it adds up to 0. Only because the currents are the same, right, in magnitude. If we had I1 and I2, then it wouldn't be 0 outside. It would be I1 minus I2, and then it would be mu naught I1 minus I2 divided by 2 pi r. But in a coaxial cable, the current in the return wire is the same as the current in the go wire. So outside the coaxial cable, the magnetic field is 0. And when we do experiments in the lab and we use the coaxial cables, right? So inside the coaxial cable there is a magnetic field, but not outside of it, right? We are outside the cable, so we're not exposed to anything. So that's it. That's all there is for the magnetic field generated by a coaxial cable that has current in it. The magnetic field is confined to the region between the inner conductor, the one along the axis, and the outer conductor, which is that shell that the current comes back in the opposite direction. So it's pretty straightforward. Yes? Yes?
So in case if I outside and I inside is not equal, which one would put the minus sign on to calculate the?
So if, suppose, give me some values, and then we'll take it from there. How big would you like I1 to be, and how big would you like I2 to be?
5 and 7.
5 and 7? Okay, so this wire, let me look at the top, only at the top. This wire has current to the right. So if I put my thumb to the right, it wants to make a magnetic field coming out, right? At the top. So this one produces a magnetic field over here coming out. This other wire over here has current going this way, it produces a magnetic field going into. So which of those two currents is going to produce the bigger magnetic field? The one with 7 amps. So I would say 7 minus 5, which is 2, but because 7 is stronger, it will be, the magnetic field will be into the board at the top. Down here, right? My fingers will be coming out of the board. So the magnetic field will curl around. If this is the coaxial cable, the magnetic field will curl around like this. Into at the top, down, behind that wall, at the bottom, coming out of the board, over here, up. So the magnetic field will curl around, and it wouldn't be zero. But because this current is the same as this current, this wire produces a magnetic field coming out, but this other shell over here produces a magnetic field going in, and since the currents are the same, then those two magnetic fields are going to be at the same magnitude, pointing in opposite directions. They cancel out and you get zero. Yes? Okay, let me do C. Maybe I'll do C first. I said I was going to do the other one, but I'll do C. It'll be quicker. So this is called a toroid, right? Toroid 3C. All right. So I'm going to erase this. So the toroid with current, doesn't say it there, but with current I and total number of turns, capital N. So I don't think I'll do as well as the picture in the notes. So I will go to the lecture notes and show you the toroid, because I think I put one in there. This is the toroid. So imagine you take a wire and you have like a ring and just wrap it around, all around you. And the current is I. So we want to know, what is the magnetic field in the hole? What's the magnetic field inside this material? What is the magnetic field outside? So what I'm going to do is I'm going to picture this as if I look this way. So the toroid will look like this. All right, and so notice how the wire is like wrapped around, right? So, but I'm only looking at the wire comes out over here, it goes down the front, and then it goes into, and then it goes in the back, like in the other room over there. Well, outside the building, comes back up, and then it comes back out over here. And then it goes, the current is this way, and then it goes down the wire in the front, and then it goes into. So this is out the board, this is into. The X means into. And then, well, there's another turn over there. Another one. And there are N. That's what this means. There are N turns. So this is like number 1, number 2, number 3, number 4, number 5, boop, 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 boop. And then, and the last one is N. And they all have current coming out on the outside, going into, and like that. So like this, like that, and like that. Do we understand that picture? No?
It's on the same wire, just.
It's the same wire. Well, I'm trying to draw this.
Yeah.
But looking at it like this, so what you would see would be this thing, That's what you would see. So this is the yellow. All of this here is the yellow part. This is vacuum here. This is the material, right? And then this is vacuum over here. And these are just wires. So there are three regions of interest. I want to calculate the magnetic field generated by this current I in each wire, right? Well, actually it's only one wire. The current is I. So we have, I want to know the magnetic field everywhere in space. I want to know the magnetic field here. Right there. I want to know the magnetic field inside this thing, and I want to know the magnetic field outside. And that's the result that we're going to derive. For one of the places. So, let's call this, I'm going to use different colors. How about I call this region number 1, region number 2, and region number 3. I'll just say region number 1. So I write down Ampere's law. Now, what is the Amperian loop that I choose in this case? So the Amperian loop that I am going to choose is, I want to know the magnetic field here, right? So I choose an Amperian loop that's a circle, a radius r. So this is my Amperian loop, the one in red. So therefore this becomes B times the length of the Amperian loop, which is what?
2 pi r.
2 pi r equals mu naught. And what's the total current that goes through this loop?
0.
0. There's no wire with current going through it, right? So therefore, in that region, the magnetic field is 0. Yes? Let me consider region number 2. So now I am going to draw this. Can I erase this now? I'm going to draw this. I'm going to erase this. I don't want to draw all of this again. So now I want to know the magnetic field here, for example, at a distance r from the center. So the Amperian loop that I choose passes through that point that is going to be a ring. It's going to be like this. This is now my Amperian loop. The one in red. Get it? So, I write down Ampere's law. And I have B times, what is the length of this Amperian loop if the radius I call the radius r?
2 pi r.
2 pi r. And what is the total current that goes through this loop? I times N, correct. Because I have, see, the wire has current this way. That current doesn't go through the loop, right? To go through the loop, it has to go into the board or out of the board, because my amperial loop is like this. My amperial loop is a vertical circle. But I have wire coming out of it here, goes down like this, which is not going through the loop, and then it goes into the loop. Once. And then it goes out over here, out over there, and then down the front, and then in again. That's 2. So you have this current going into. Each current is I, and I have N turns. So the total current that goes through the loop is N times I. Where I is the current in the wire, and N is the number of turns that are going into the loop. Right? And the next one is the answer. That's the answer. This is the expression that I have in my notes. Mu naught capital N I divided by 2 pi R. And if I consider region number 3, which is outside the whole thing, right? Then in that case, my amperial loop, if I want to know the magnetic field over here produced by this current in this toroid, my amperial loop is going to be like this, right? That will be my amperial loop. And so I write down Ampere's law. And so this becomes B times the length of the amperial loop around, which is, I'll give it a radius R. Now, what is the total current that goes through this amperial loop in blue?
0?
0. Why?
Because half of it is going out and half of it's going in.
Oh, yes. Or you have, like, going out, we have 1, 2, 3. We have Ni going out. But we have Ni going in. Well, if one of them is out and the other one is in, one of them is positive, the other one is negative. So you take the difference between them and you get 0. So the magnetic field is confined to the region, the magnetic field is confined to this region here. And the magnetic field is, at all points, tangent to this amperial loop. Right? In this case, actually, think of it like this. The current comes out over here, goes back in over here, so the magnetic field is going to be this way. The magnetic field is tangent to this ring. Tangent. Tangent. Right? Inside, the magnetic field will be this way. That's the toroid. So notice, boom, boom.
Since it cancels out in region 3.
Since what?
Since it cancels out in region 3, why doesn't it cancel out in region 2? Since wouldn't it go down and come back halfway at least and still be?
No, the ring is like this.
Mm-hmm.
Hard to see it.
So the ring is like this. Let's say that's the amperial loop. So the current, so all I'm interested in is in the current going through this thing, either this way or that way, but through it.
I think
But the wire comes from, when you consider the region number 2, the current is out over here, which is not going through it, so that doesn't count. It goes down, which that's not going through it, but then it goes in. That's I.
Mm-hmm.
And then it wraps around, goes up the back, above, which is not going through it, and then it goes in again. That's 2I. So every turn has an I.
So we're
it's
only interested
capital
in
N
what's,
times I.
we're only interested in what's going through.
Yeah, it's the so you imagine a loop.
Yeah.
And the I enclosed means the current enclosed by that loop, the current going through the loop, the net current going through the loop. Now, if you consider region number 3, every wire that has current coming out this way through the loop goes back in through the loop as well. So it's like this one gives it a plus I, and then this one gives it a minus I, so they cancel out. You have N wires coming out through the loop, but N wires with current out, but also you have N wires going through the loop in. So you have Ni minus Ni, which is 0. Yes?
The magnitude constant within that.
It depends on R. So if you make this very small, then you can approximate it as being constant, but it depends on R. The closer you see, there's an R dependence in region number 2. So the farther away you are from the center, like if you consider a point over here compared to a point inside that's over here, this is a stronger magnetic field because you're divided by a smaller R. This is a smaller magnetic field. So there's an R dependence. So it's not uniform. But if this radius is big and this is very thin, then over that thin region you can approximate it as being uniform.
How about the diagram of the, when you draw the diagram for the wires, how it's changed within the B versus R?
Mm-hmm. Yeah, if I were to draw that, I would draw something like this. Right, so let's call this, you can call this if you like radius A and the other one B, just to give it radius. So this is A and this is B. Right? This is R. And this is magnetic field. So in this region between 0 and that's 0. And outside this is 0. And it behaves as one over R. Some numbers divided by R. So this thing is going to go like this. Something like that. That's what it's going to look like. Zero, 0, 1 over R. Can I erase it?
Yes.
And that is what this picture is trying to show. So this was region number 1, path number 1, path number 2, and path number 3, I guess. So the thing in blue is what's over here in yellow. So for region number 1, right, none of the wires have current through it. There's no wire through this ring, through this apparent loop, so the magnetic field is 0. But if your apparent loop is inside this thing, which they should have used the same color here as there, but this thing, is this. In here, right, you have these wires with current going into, you have N of them, N times I. But then, if you can draw an Amperian loop on the outside, outside over here, every wire that goes in goes out. Goes in, out, in, out, in, out, in, out, in, out. The net current through it is 0. So the magnetic field outside is 0. That's what this picture here is attempting to show. So I'm going to do the solenoid, which is one that I still need to solve in this set of examples in chapter 28.